Hello, my name is Nicolas Cardoso and today I'm going to talk about the work we have been doing on adaptive behavior for IoT environments together with my colleagues Jairo Ariza, Kelly Garces, Juan Pablo Rodriguez and Fernando Jimenez at Universidad de los Andes in Bogota, Colombia. Our work is dedicated to the development of an IoT architecture tailored to adapt to transient devices as a means to increase the robustness of the systems and applications in the IoT environment. The Internet of Things is the enabling technology to facilitate our everyday lives and realize a wide range of services as those put forward by smart city initiatives. The IoT allows us to be continuously interconnected, gathering information from our surrounding environment through sensor devices and taking action based on sensed information through services and actuators. However, the IoT is not currently without problems. Continuous connectivity and sensing and actuating in the environment is a difficult task, as the environment continues changes as we roam around. Additionally, the natural evolution of the environment also poses a challenge in keeping connectivity between services and devices up to date. To address the existing problems in the IoT environments, we put forward 8 challenges in building IoT systems related to the adaptivity of such systems. This work was presented as UCAMI 18 as a research agenda push forward for IoT systems in the future. In particular, in this work, we are going to focus on the first 2 challenges, that is, dealing with failures in devices and in services and devices that cause transient disconnections of the system to ensure that resiliency of the IoT system. We must assure that the system is capable of dynamically adapting to those changes. The second challenge comes as a result of the environment evolution, where new devices may appear and disappear unannounced from the environment, and should be taken into account in the system already executing without disruptions. These 2 challenges correspond to the natural behavior of IoT systems in which we identify 4 main characteristics to address in order to build effective IoT systems. First, IoT systems are highly dynamic. This means that they must take into account that devices are transient and not long-lasting. That means that devices are only in the environment for a short span of life. It is up to the devices to discover the most suitable devices for their functioning, and due to intermittent interaction between services and devices, services are prone to errors. Our main goal with this work is to build an IoT architecture readily available to manage discovery of IoT systems as means to increase their resilience. As a case study and a prototype to evaluate our adaptive architecture, we use a sustainable urban drainage system controlled using an IoT system. The system is composed of a drainage area that is able to collect and keep rainwater. However, to avoid overflowing the system and nearby areas, the system is controlled by different sensors that regulate the level and quality of water in the system. The system is controlled to a web service that gathers the information from the sensors and can take actions according to said information. So, for example, if the sensors sense that the level of water in the storage area is too high, we can release part of the water to avoid overflowing the system. However, in this system, we identified from different environment sources causes that can compromise the behavior of the system and as a consequence flood the nearby areas. Environment conditions as well as the devices can cause problems. For example, in the case of a device battery is depleted, then no information from that device will be sent to the system and in turn break the behavior of our web service. Connectivity intermissions in the data transmission channel between the sensors and the web service can cause information to be lost and therefore for the service not to work properly. And finally, other external sources as security attacks can compromise the integrity of the information collected by the system and in turn the behavior of the system. To deal with these situations and avoid failures, we put forward a process consisting of 3 steps in the development of IoT systems as part of our architecture. First, we integrate a concrete and expressive description of services and devices in the environment, capturing their functionality and non-functional characteristics. This specification gathers both services, and devices as one single entity. Second, we need to enable autonomous connection between IoT devices to enable the reconnection of transient devices and the discovery and connection of new devices. And finally, we require a technique to manage the connection between these services and devices dynamically, always maintaining the most appropriate behavior for the system. First, to describe IoT entities, we use an ontology-based approach. Our proposal puts together aspects of three different ontologies to entirely describe the environment of IoT system. Our ontology includes the SSN ontology as a way to describe the physical aspects of the environment with the sensors and actuators, so the IoT devices. The SIO ontology is used to describe the services provided and required by the system. And the quality of service ontology, which is proposed by us, is used to describe the quality parameters of services and devices. These ontologies are used to fully describe the entities in the environment, so both services and devices. Note that here, for example, on the left, that sensors are treated as physical services to unify the connection interfaces between both services and devices. We use the SSN ontology to describe properties about IoT entities, so IoT, both services and devices. The purpose of this ontology is to characterize the capabilities of IoT entities, and such characterization will be used to help us discover the best match available between services and devices. The QoS ontology, which is part of our proposal in this work, is used to characterize the quality of service parameters for each of the IoT entities. Similarly to the SSN ontology, we use this ontology as a means to characterize the best available match between the services and devices. Second, to manage the autonomous connection between IoT entities, we design a completely automated process to match services and devices in the IoT environment based on their description, that is the ontology specification that we just described. This process consists of three main steps: executing a functional matching of the different entities, and non-functional matching of their properties, and a quality of service matching to describe the best suited pairing between services and devices. Additionally, we keep track of the known services by means of an execution guidepost, and this helps us to dynamically change to the best suitable behavior for our web services. The functional matching process explores required capacities for services and compares them with those offered by devices in the environment. As an example, let us take a rain service for our case study, requiring rain information given in a unity of millimeters. And let us suppose that we have 4 different meters, so 4 different devices, as we show here in the slide, that are providing information to the web service. Additionally, we want to match services that give us a quality threshold over 1.4, which is set by the service providers as a metric of information fidelity for the devices. So if we look at the 4 services on the slide, we see that the first service is a perfect match for the first device is a perfect match for the requirements of the service. That means that this meter is providing a category with a range that provides units in millimeters as we require. As a consequence, the score of this service is 2. If we go to the second meter, as the units provided by the meter are not an exact match, but we can have an automated conversion of the units between inches and millimeters, then we obtain a lower score, but still a score that is over the threshold. The case for the third and fourth meters gives us scores lower than our threshold, given that the category or the unit provided by that meter does not match to our requirements. Our non-functional matching works in a similar way to the functional matching we just described, this time taking into account non-functional properties of the devices. As with the previous case, the service provider defines a given matching threshold and evaluates the required properties against the meters available in the environment, and in this case we also have 4 meters in the environment. So now we have to evaluate these two properties that are significant for the service provider, so accuracy and availability of the meter. As before, we do the evaluation with the 4 emitters available in the environment, in this case obtaining a match that goes over the threshold just for meter 1, while meter 2, 3, and 4 give us a lower score, lower than the threshold, given that either the accuracy or the availability does not match that of the required service. The final step in our process, and the one that provides the adaptivity to our IoT architecture, is the execution guidepost. As multiple matches may exist between services and devices, the execution guidepost keeps track of all of these matches, making sure that the selected match, so the selected pairing between a service and an IoT device, is the one that is with the highest score. So in this example in the slide, we see a match for a range service with different 5 meters. And here only 2 of those meters, meter 2 and 3, are available in the system. So for these 2 meters, we choose the one with the highest score. As both meters have the same score, then we just choose either of them. What makes our architecture adaptive through the execution guidepost is that when the situation about one of these devices changes, so it may become available or unavailable dynamically, then we can choose to the next best matching. So in this case, for example, if meter 1 becomes available again in the environment, then and it provides a higher score than the other matches, then we dynamically change to pair our range service with this particular meter. Our complete architecture to ensure the resiliency of IoT services and devices is structured as shown in this slide, and is available to test and use at our GitHub repository shown at the bottom of the screen. All the details of the components are presented in the paper. We here are just going to talk about the main components used for the discovery and the matching of the services. So the first part of architecture concerns the components used for the discovery of the entities in the environment, abstracting away the specific communication protocol using the OM2M architecture. The discovery components are in charge of detecting relevant entities for the system by using the ontology manager. So when a new device is detected in the environment, these components will add it to the ontology manager to be able to match. Actual entities are matched through our matching components. And in these components, we use the matching algorithm that we just described, the matching process that we just described, and the instance matching ontology manager for knowing which devices are available to this particular service. As a consequence of these two pairings of the components, the inclusion of devices and services in our system is the result of both the discovery phase using the discovery components and the matching phase using the matching components of the architecture. So this enables us to include new devices and to be able to dynamically change the pairing between services and devices using the execution guidelines. So we evaluate our proposed architecture from 2 perspectives. First, we measure the correctness of our matching algorithms to make sure that the requirements of a service are actually satisfied by the IoT devices provided in the system, and then we measure the performance of the system itself. To evaluate the correctness of our matching algorithm, we use a dataset from the Ontology Alignment Evaluation Initiative. This dataset consists of 3 different ontologies: Memory Alpha, Star Trek EU, and Memory Beta, evaluating the pairwise matching between the 3 of them. The characteristics of each of the ontologies vary in size of their instances, describe properties and classes to take into account different variations of the dataset. We evaluate against 3 of the approaches used in the competition. We present the results for the F measure subsumming both the precision and recall results. The disaggregated results are in the paper. So, based on these results, we can conclude that our algorithm presents a better precision for the first 2 ontologies, while a lower precision is observed in the third ontology. The cause of this is that in the third ontology, the descriptions are longer, and our functional matching works best using short sentences as descriptions. Our algorithm in general presents a suboptimal recall when compared to the other algorithms. This is due to the optimistic approach we used on the syntactic matching similarity method, while the other matching algorithms use multiple matching methods. The performance evaluation for our system consists in a simulation of the load of IoT systems with services and devices generated with respect to the actual physical characteristics of real-world devices. So we generate 10,000 sensors and 1,000 services to evaluate the performance of their matching. The generation of these services and devices are based on the actual physical and logical constraints of our case study. As it is possible to observe from our functional matching, the performance deteriorates rapidly as the number of sensors increases, requiring up to 9 seconds to perform the matching when 10,000 sensors are present in the environment. The cause of this delay is due to the amount of comparisons required to evaluate the functional properties of the services with all the available sensors in the environment. In addition to the performance of the functional matching, we measure the time to include a device into the ontology. So when a new device appears, as well as the time required to manage the execution guideposts to dynamically change the pairing between a service and a device. In both cases, we observe that the behavior of the growth as more devices are added into the system is good. In the particular case of the execution guideposts, we see that in the average case, we can see a constant execution time, meaning that the cost of actually adapting to the best possible pairing between a services and a device is not significant in the execution of the system. So, to conclude this presentation, we want to highlight the main contributions of our work. First, we defined an adaptive and robust architecture for IoT systems designed to address the 8 challenges for building IoT systems. In this work, we addressed the first 2 challenges, but we have addressed all 8 challenges using our proposed architecture in other work. To foster adaptivity to different situations, we use the execution guidepost, enabling the rapid connection and disconnection to different devices in case of transient failures. So this characteristic is the main driver of our adaptations. Our approach constitutes a step forward in the inclusion of devices, including a greater number of properties into the matching algorithm, creating IoT systems more aware of their environment in full. And finally, our matching algorithm is configurable to best suit the different application domains. Future research perspectives in this particular line of work include improving on the performance of our matching algorithm to provide better response and smooth behavior for user applications, and the focus on the discovery of the matching components to integrate the solution presented to the other 6 challenges for the IoT systems. We want to thank you for your attention to our work.